Okay, right. Welcome back, everybody. And now we are going to discuss the white bundles present inside each of the cerebral hemispheres. We have already finished with the discussions of all the surfaces of the cerebral hemispheres, the superolateral, the medial surface, and the inferior surface. We discussed that. But all the same, we are going to also be referring along these surfaces while we are discussing both the internal and other external structures that we are yet to discuss. So, from the introduction of the neuroanatomy, I think I told you that the basic components of nervous tissue in general is both gray and white matter. So, along the line, we also discussed what is the meaning of gray matter and what is the meaning of white matter, what is the meaning of nucleus and ganglia. Together we have discussed all this. So, and you can also remember that we have discussed the different varieties of fibers that we have in the cerebral hemisphere. We discussed three categories of fibers, the white matter bundles, where we discussed the conventional fibers. I'm sure you can remember that. We also discussed the association fibers. And we also discussed which one? The projection fibers. And these are the three different categories of white matter that we have discussed. So, if we now take the association fibers, if you can remember, we talked about only which one? The short and the long association fibers. That was where we stopped. So since we are now going deeper part of the neuroanatomy, now we see the different types of the short and the long association fibers, what we term or call white matter bundles. So the white matter bundles, some of these bundles that form association between one lobe of the cerebral hemisphere with other. That's what we are going to discuss. So if you now look at the medial side of the cerebral hemisphere and you cut across the medial side and then you expose the white matter, because if you look at the medial side of the cerebral hemisphere without cutting the sagittal section across each of the cerebral hemisphere, that is the only time when you are going to see these bundles. But otherwise, if you divide the two cerebral hemisphere in the longitudinal fissure and then you look at each of one either on this side or on this side, you are not going to see these bundles. So until you now separate the two cerebral hemispheres into two, left and the right, and then you now, along the right or the left one, you now make a parasagittal section, and then you remove this part, and then you look at it on this part, then you'll be able to see this. That means these bundles are inside the cerebral hemisphere. So these white matter bundles, those that form association, either long or short, they are of different categories. There is one very long association between the frontal lobe, the parietal lobe, and the occipital lobe. Probably at times it may also extend into the temporal lobe. Are you clear? But still this association is within the same cerebral hemisphere. Are you clear? That is association fibers. So this one, because it is long, commences from the frontal lobe, passes across the parietal, also passes across the occipital, and then it also extends into the temporal lobe. That is what we call superior longitudinal bundle. We call it what? Superior longitudinal bundle. And this is one of the longest, or I can say is the longest association fibers that we ever know. So we have what? Superior longitudinal bundle connecting all the lobes together. Are you clear? Good. Another bundle inferior to the superior longitudinal bundle is what we call cingulum. Cingulum is just like a bundle of white matter fibers connecting the frontal lobe and some part of the parietal lobe within the singular gyrus. You get it? So because it is within or along the singular gyrus, that is why it is called cingulum. And that one doesn't extend into the temporal or the occipital, but rather it only connects the frontal as well as the parietal. Are you clear? Good. There is also another white matter bundle that is lying directly inferior to this cingulum. And that is what we call fronto-occipital bundle. This fronto-occipital bundle is similar to the superior longitudinal bundle in that it also connects frontal lobe, passes across the parietal lobe, and also connects the occipital versus the temporal. At times, it may only connect the frontal and the occipital only without passing into the temporal. But again, it may also do the same as the connection of the superior longitudinal bundle, but mainly its own connection, it is between the frontal and the occipital. And that is why it is called fronto-occipital bundle. Are you clear? This is also long association fibers. So now how many long association fibers do we know now? 3. Superior longitudinal bundle, cingulum, and the fronto-occipital bundle. Similarly, below here, there is another association fibers that is lying within the temporal lobe. It begins from the occipital lobe and passes into the temporal lobe. That one connects the occipital with temporal. Probably this will rather be called occipitotemporal bundle, right? But in most of the textbooks, it is called inferior longitudinal bundle. Are you clear? So if you call it occipitotemporal, it's still not bad. It's okay. It makes sense. But all the same, its own name is inferior longitudinal bundle to maybe commiserate with this superior longitudinal bundle. Since we have superior here, because it is located in the inferior most part of the lobe, and that is why that name is given inferior longitudinal bundle, and because it is just lying also longitudinal, not horizontal. Probably maybe the way I drew it, it looks like a horizontal bundle, but all the way it is longitudinal like that. It's not all that horizontal like the way I drew it. So now we have seen how many? 4. The 5th one is a curved, arched fibers like that. So they now connect the frontal lobe like that with the temporal lobe. So the fibers arch from frontal down to the temporal. Although this one, they are supposed to be short association fibers, but unfortunately they are also considered to be long association fibers. So they connect one lobe and another lobe. Probably that is the reason why it is called a long association fibers. If you can remember, the short association fibers, you connect adjacent gyri. You get it? For example, now if maybe this is just a gyrus here. This is one gyrus. This is another gyrus here, or gyrus. So we have gyrus number 1, we have gyrus number 2. So these short association fibers, they connect this and this. So since they connect adjacent gyri, that's why they are short. But this one, they connect lobes. Do you see the difference? Probably that is why most of the anatomies, they consider this as long association fibers, because they connect lobes, not gyri. The short association fibers, they connect adjacent gyri together. and that's why they are short. So they are called short association fibers. And this one, they connect lobes, one lobe and another lobe. And that is why they are called long association fibers, because they have to travel far before they connect one lobe and another. Although this oncinate is called oncinate because it connects frontal lobe with the temporal lobe, and it's just around the anchor side. If you can remember, we discussed about the uncus around this temporal lobe, so it arches over that side. So this is the oncinate. So on the medial side now, these are the most important or the prominent white matter bundles that we can see. We can see the short, we can see the long. And so for the long ones, these are the ones that we can see. So we can see 5 of them when we cut a cross section, the parasite section across the cerebral hemisphere. So now we have seen this. The other ones that we will also discuss, the association fibers after that, is the commissural fibers. Commissural fibers are there also when you cut across the cerebral hemisphere on the medial side, or when you make a horizontal section like this, and then you remove the top, and then you look at it from above, and that is this. So you now make a cross section of the cerebral hemisphere, the two of them together, and then you remove the top of both the left and the right, and then you look at it from the top, and this is what we are going to see. So when we now take this horizontal section, we remove it. So we are going to see the two cerebral hemispheres, the left one and the right one. So the white matter bundles that we are going to see after that, when we make that cross section, is what we call the commissural fibers. The most important one is the corpus callosum. So this is what? This is corpus callosum. So this corpus callosum, in this view, you are going to see that there are fibers of this corpus callosum connecting identical areas of the right cerebral hemisphere with the identical areas of the left cerebral hemisphere. So they must pass horizontally across the cerebral hemispheres. Are you clear? So these fibers, they form the body of the corpus callosum. So this one forms what? The body of the corpus callosum. So this body is formed by these horizontal fibers connecting identical sections of the right with that of the left. And then anteriorly, if this is the anterior aspect of the cerebral hemisphere, this one, and this is the posterior aspect, this is my back. I did like this, and then I look at it from the top, I put it like this. So we have some fibers connecting right cerebral hemisphere, frontal lobe, and come and connect identical area of the frontal lobe of the left side. Are you clear? So frontal lobe here of the right side, frontal lobe here of the left side. So these fibers, as they arc like this, so they are called forceps minor. Are you clear? And there are also some fibers from at the back. So they connect occipital lobes of the right side. Occipital lobe of the right side connects the occipital lobe of the left side. So they act like this. Because they are larger than these ones, so they are called forceps major. Are you clear? Major means big, minor means small. So those fibers connecting frontal lobe, the two frontal lobes together, they are forceps. They form the fibers of the forceps minor, and this one they form the forceps major. Are you clear? Good. And so now, when you now cut a cross section of cerebral hemispheres in the longitudinal fissure like this, that means this midline section, and then you look at it from this side. This is the diagram you are going to see. Are you clear? So here you are going to see the corpus callosum, the cut section of the corpus callosum. So when you now look at it, I just remove it from here, and then I do it alone. So you can see that anteriorly, this is the anterior aspect, and this is the posterior aspect. So here in the anterior aspect, you will see one bend like this of the corpus callosum. And this bent aspect of the corpus callosum is what we call the genu of the corpus callosum. It's just like when you bend your knee like this. Knee, it means it is meaning genu in Latin. So from the knee, because of this bending, this place is called genu. And this aspect that passes down from the genu, this is what we call the rostrum of the corpus callosum. And this side is the body of the corpus callosum, and posteriorly here is what we call the splenium of the corpus callosum. So it means that fibers that will be going, connecting the frontal lobe of, if this is the frontal lobe of one cerebral hemisphere here, and this is frontal lobe of another cerebral hemisphere on this side, if these fibers want to come and join this, so they must pass across the genu and the rostrum of the corpus callosum. And those ones that, connects the two cerebral hemispheres along the parietal region like that, so they pass through the body of the corpus callosum. And those one, if this is the occipital cortex here, and this is also the occipital cortex of this one, if this one wants to connect, from here, connecting this one, so they must pass through the splenium. So the forceps minor, they must pass through the splenium of the corpus callosum, while the forceps minor, they must pass through the rostrum and the genu of the corpus callosum, while those ones that pass horizontally across the parietal region, connecting the identical areas of the parietal region, they pass through the body, or they form the body of the corpus callosum. So we have now seen the parts of the corpus callosum. On the medial section, we will see the rostrum, we will see the genu, we will see the body, and we will see the splenium of the corpus callosum. When we now make a transverse section of the cerebral hemisphere, we are only going to see the forceps minor horizontal parts of the body of the corpus callosum and the forceps major of the corpus callosum. Are you clear? So these are the sections, two sections, for you to be able to appreciate the corpus callosum. Apart from the corpus callosum, that has been the biggest or one of the prominent commissural fibers, in the last video we also discussed another commissural fibers, the fornix. So this fornix is just like a C-shaped structure. C-shaped in the sense that it begins from one area like this and arches over from the front, backward, upward, and then forward and downward like that to form a C-shaped structure like this. And this fornix, one on either side, they unite together toward the anterior side of it. So the fornix begins from hippocampus. If you can remember, in the last video we discussed the para-hippocampal gyrus. So the para-hippocampal gyrus is by the side of the hippocampus. If you can remember, I told you that you have to open up the para-hippocampus before you see the hippocampus. So now we remove the para-hippocampus, and that is why we can see the hippocampus. So from the hippocampus, there are some axons from the neurons here. So neurons in the hippocampal gyrus, they pass backward like that, they form a bundle. They pass upward like that, they pass backward initially, then upward, and then forward, and then downward to terminate into two mammillary bodies that I discussed before. If you can remember in our drawing in the last video, we discussed the two mammillary bodies that lie in the interpeduncular fossa. So this fornix, as it begins from the hippocampus, it passes backward initially, then upward, then passes forward, then downward and backward again to enter into the mammillary body. That is phonics of one side. The other phonics from the other side, it also begins just like the way the other one begins. So in the other cerebral hemisphere. So it passes from the hippocampus of that cerebral hemisphere. This is the left one, this is the right one, for example, this is the left one. So it passes the fibers of these neurons in the hippocampus here, they pass backward, then upward, then forward, then they pass downward, and then a little bit backward, and enter into that mammillary body on that side. But along the line, the left and the right, they fuse together anteriorly. Are you clear? So where they unite, that is why we call the body of the phonics. Are you clear? So by the time they unite, they act as if they are one. While in the real sense, they are not one. Each one is separate, but then they unite along the line. And so this is the body of, so just anterior to the body of these two phonices, singular phonics, and plural we call it phonices. Phonices. F-O-R-N-I-C-S. Phonices. So anterior to the body of this union or fusion of these two phonices, you have what you call the columns of the phonics. So this is the left column, this is the right column. And so each one ends or terminates into the corresponding mammillary body. So here also there is a union of this, two phonices together by a commissure. You understand? And so at the back here, where they begin from the hippocampus, this area of beginning here is what we call the crus of the phonics. So as it begins from the hippocampus, passes backward and upward, that is what forms a crus of the phonics. Plural, crura. And so that is why you saw me writing it in plural, because I labeled the two together. Singular, crus, and plural, crura. So that means each of the phonics begins with a crus, passes upward and unites with the other with the other phonics to form the body, and then the body now divides anteriorly into right and the left columns, and then each of the columns now terminates into the corresponding mammillary body. Are you clear? Good. What I should also add is that on the surface of each of the hippocampus, there is also a white matter bundles that also contributes in the formation of the phonics. And these white matter bundles lying on the surface of the hippocampus, they are called alveoli. So they pass through into the phonics. When we discuss the circuits, because there are so many connections, you will see, or we will still refer back to this phonics and its own details. You see, the hippocampus is called hippocampus because it looks like a seahorse. So from the Latin, seahorse is called hippocampus. So, and that is why the name hippocampus, because it looks like a seahorse. And so the phonics begins from the hippocampus, forms crus, then unite with the other phonics to form body. The body now divides into right and the left columns. Each one terminates into the corresponding mammillary body. We'll see its own function when we come to discuss. Now we've seen the commissure. These are not the only commissure of importance that we discuss. There is also anterior commissure, there is also posterior commissure, there is habenular commissure. We have so many commissures with regard to these commissural fibers. But then the most important ones that I want you people to understand or to take note of is the corpus callosum and the phonics, because they are the most important. Others will just mention them when we come across discussing other things like that, when we go deeper. We will come across them and we will just mention them. We'll see where they are and then we pass. But these are the two most important ones that you people should give more attention to. The other one that we'll discuss is the projection fibers, which, if you can remember, we discussed about the projection fibers. So the projection fibers, if you can remember, in our last videos, we said these projection fibers, it is axons of the neurons from the cerebral cortex. So they now radiate from different parts of the cerebral cortex. They now descend down. As they descend down, they now form a bundle of fibers. So that means from radiated fibers, this one comes like this one comes like this one comes like this, and the other one comes like this. At the end of the day, they now form a bundle of fibers. And then finally below, they now unite to form something like this. So as they form this bundle of fibers here, the bundle of fibers, as they descend down like this, before they are just radiated like this. You get it? In a radiated fashion. And so later on, after radiating like this, so they now descend, they form a bundle. And this bundle is the one here. And because this is a coronal section, when you cut across cerebral hemisphere like this, and then you look at it from the back, this is what we are going to see. Are you clear? So when you look at it, that is what we are going to see like this. So this bundle that is being formed lies in between some important structures. On the medial side, this bundle of fiber is what we call internal capsule, because it encapsulates certain important structures. When we say a capsule, that means it surrounds, you get it? Just like you put a blanket over you. So you are encapsulating yourself. So here, the bundles, they surround important structures here. And these structures are, number one, the thalamus. So we have thalamus on the right side, we have thalamus on the left side, enclosed by this internal capsule. You get it? These two thalami, singular thalamus, plural thalami. So we have the two thalami enclosed by this internal capsule of the left and on the right. Similarly, we have another nucleus that is lying immediately above each of the two thalami. And this nucleus is what we call caudate nucleus, which is part of the basal nucleus that we will discuss later on. Are you clear? If you can remember, we said that in the nervous system, we have both white matter and gray matter. And the gray matter can be from outside or from the inside. From the inside, that is what we call nuclei, singular nucleus. So these are all intracerebral nuclei of importance that we will discuss. So in general, this internal capsule is just a conglomeration of the radiated fibers that emanate or emanated from the neurons of the cerebral cortex. So as they come down, as they descend down like this, they form this. If this is just a sheet of bundles of fibers, so these fibers, they now bend like this. It bends like this. This is the midline. If I'm just assuming like this. So if these fibers now, as they come and form this bundle, initially they are flat. But because there is one large nucleus on the lateral side of these bundles of fibers as they descend, they form this bundle, internal capsule. So there is a nucleus that is lying on the lateral side. This is the medial side of the internal capsule, and this is the lateral side. So now, this nucleus, what we call the basal nucleus, during development, it indents, it pushes these bundles of internal capsule towards the midline. So much so that this flat sheet of bundles of internal capsule, it bends so that it forms an anterior limb. If this is the anterior side, and posterior limb, if this is the posterior side. So that if you now cut across the cerebral hemisphere like this, and then you remove the top, you look at it from the top, you are going to see that the internal capsule forms something like a B-shaped structure like this on either side, because there are two. Because we have two cerebral hemispheres. So it is going to be like this. Are you clear? Because this nucleus, the basal nucleus, now pushes the initially vertical fibers so that it has a genu towards the midline. Are you clear? So that is it. So now we've seen that we have this internal capsule, and so the internal capsule now has anterior limb, posterior limb, and the genu, just like your knee, bent. You understand? Because it bends, that bending, just like the knee of, so it is called a genu of the internal capsule. So internal capsule has how many parts? 3. Anterior limb, genu, and posterior limb. All these fibers that descend, if you can remember last time, we discussed about the human homunculus, didn't we? Good. So those fibers that are coming all the way from all the limbs and the trunk, they pass through the posterior limb. If I now shed this line here, this is just the internal capsule like this. All right? And so this is the genu here. So all those fibers coming from the head and neck, coming from the neck, the trunk, and the limbs, upper and the lower limb. All these fibers coming, if this is the human homunculus, you know, on the medial side we said what? We said the limbs, right? The limbs are located here. Lower limb, right? Here we have the trunk, right? Here we have the face, right? This is the face, right? And this is the larynx, pharynx, and the tongue, right? Good. So now this is we have the hand here, hand and the upper limb. So all these fibers coming from the lower limb, from the trunk, from the upper limb and the hand. Are you clear? So unfortunately this is vertical. So they now descend all in this posterior limb. Are you clear? So all those fibers here, these ones, they now bonded together. And then they now pass into the posterior limb. And those fibers from the face, they pass in the genu of the internal capsule. While those fibers from the other areas of the cortex, they pass into the anterior limb. So that means virtually all the different parts of the body that is concerned with the motor activity, you know, they pass through the posterior limb and the genu. The genu contains fibers from the face, the corticobulbar fibers from the cranial nerves that we have discussed before. If you can remember, we discussed about the facial nerve supplying the face. The trigeminal nerve also supplying taking the sensation from the face. All these are cranial nerves. Are you clear? So all those, they pass through the genu. So the corticobulbar from the cortex, you know, carries motor activity, serving motor activity of the face, they pass through the genu of the corpus callosum, while other part of the body, the neck, the trunk, the lower limbs, the upper limbs, and what have you, they all pass through the posterior column. So the whole human body lies between the genu and the posterior limb, while the other part, the anterior limb, is other ascending tracts that carry sensation, thalamocortical, corticothalamic, frontopontine, all those fibers, we'll discuss them. But most important ones that you are supposed to remember are fibers that serve motor function to the face, the trunk, and the limbs. Are you clear? Good. So now we've seen that what are the relations of this internal capsule when we now cut a cross section like this. This is coronal section. So in this coronal section, you will see that above the two internal capsules, they are separated from each other by corpus callosum. You see, this is corpus callosum, connecting this cerebral hemisphere with this cerebral hemisphere. On the medial side of the corpus callosum, you have a thalamus of that same side. And on the lateral side of that internal capsule of that side, you have the basal nucleus. You get it? So that means on the medial side, we have thalamus, we have caudate nucleus on the medial side, and on the lateral side, you have the basal nucleus. Are you clear? Okay? And so there's also external capsule here, lying, behind the basal nucleus. So the most important structure that you should know that related to the lateral side of the internal capsule is the basal nucleus. I told you that basal nucleus in other textbooks, they call it basal ganglia. You understand? So which I think is wrong to call it a ganglion, because we have already defined what is a ganglion. Conglomeration of cell bodies outside. So if you call this one ganglion inside the cerebral hemisphere, what are you saying? So it means you have to redefine what is a ganglion. You get my point? And that is why most of the anatomists, they no longer call this basal ganglion or ganglia. They call it what? Basal nuclei. Are you clear? So as these fibers of the internal capsule descend down, they all pass through the midbrain, the brainstem. And I told you before that the brainstem consists of midbrain, pons, and medulla oblongata, which is this one. So as they descend down, if you can remember while I was discussing the inferior side of the cerebral hemisphere, I discussed about the cerebral peduncles, these bundles that they descend from the internal capsule. So as they descend from the internal capsule here, this is the internal capsule here, so it descends into the internal capsule. So from there, here, they enclose that fossa at the inferior surface as they descend down. So if this is the inferior surface, so as they come down like that, so they now form this fossa in between themselves. So as they continue down into the pons, and so they descend down into the medulla oblongata. In the medulla oblongata, each one crisscrosses. Major part of it crisscross. Did you hear my point? About 80 to 85%. 80 to 85% of these fibers, these descending fibers, they crisscross in the medulla oblongata to the opposite side. So if this is the right descending fibers from the right internal capsule, as they come in the medulla oblongata, they now descend, they now crisscross to the other side. So from the right, they go to the left. The same thing with this one. So here they form what we call pyramidal decussation, because these are the fibers from the pyramidal cells of beds of the cortex. And so we have this pyramidal decussation at the medulla oblongata, lower aspect of the medulla oblongata. And so that is why you see that the right controls the left, or the left controls the right, because of this crisscrossing of these fibers in the lower part of the medulla oblongata. Are you clear? So it means that the remaining 15 to 20% of the fibers, they go uncrossed. That means those from the right sides, they go directly downward into the spinal cord without going into the left side. Similarly, on the left side, those remaining 15 to 20%, they also go uncrossed and they go to that same side. So we have ipsilateral fibers and then we have contralateral fibers of the pyramidal tract in the medulla oblongata. The majority of these fibers is what? The decussated fibers, which are 80 to 85, while the undecussated one are the 15 to 20%. Are you all clear? Good. This, they go into the spinal cord, and then we will see where they terminate when we now come to discuss the spinal cord. Are you clear? Good. So I think we will stop now, and so next time we are going to discuss the intracerebral structures. Now we've finished with the white matter bundles of the cerebral hemisphere. So the next one that we are going to discuss is the intracerebral structure. That means we are going to discuss the basal nuclei. We are going to discuss the thalami or the thalamus. We are also going to discuss the hypothalami or the hypothalamus singular and other important intracerebral nuclei. And we are going to take each one by one and discuss it so that you people will understand every bit of it.